Uh, yeah, I think this works. So yeah, thank you for the organizers for organizing this very nice workshop, and thank you for attending this part. During this talk, I will talk about essentially two papers that were published in the last year or two. They may seem somehow unrelated. I mean, the link between them is essentially showing learning separation, that is quantum advantage in a learning scenario between classical and quantum learners. But they will apply in essentially quite different regimes. One is like polydepth, and the other one is shallow, like constant versus super constant depth. This work was done in collaboration with people at the University of Leiden, at the University of Berlin, where I'm currently affiliated, and TU Berlin, and also, while I was doing my PhD at the University of Innsbruck. Okay, so a bit of introduction about quantum machine learning. Just give you my view on it, on what happened in the last 5 to 10 years. Personally, I kind of saw kind of a paradigm shift in what people are interested in quantum machine learning. Before 2018, people were mostly talking about these HHL-based quantum algorithms. So HHL, for those who don't know, it is a quantum algorithm that allows you to do matrix inversion in simplest form, but essentially a bunch of linear algebra. And it kind of promises under a lot of like fine print exponential speedups for doing this kind of linear algebra tasks. And given that linear algebra is kind of ubiquitous in machine learning, naturally it finds a lot of applications there. And for a nice review article about this that actually was published end of 2017, kind of lists a bunch of these HHL type algorithms in quantum machine learning. And beginning of 2018, actually in the first few months of 2018 on Archive came out a bunch of papers that try to dig into kind of a more heuristic approach to quantum machine learning without now losing like the guarantees of computational speedups, and more looking into something that can be more applicable in the NISQ regime, noisy intermediate scale quantum regime, where people now essentially take an approach similar to what you would do with deep neural networks classically. They would take parameterized quantum computations where some of the parameters are used to encode data and some other parameters are left to be variational parameters. And through quantum evaluation and a classical optimization algorithm, you would train these parameters to essentially try to fit your function behind a machine learning task. And here about terminology, I would just like to mention that what we call quantum machine learning models, some people would call parameterized quantum circuits, some other would call them variational quantum circuits, or a term I like a bit less, which is quantum neural networks. They all talk about the same thing. It's just a parameterized computation with data, potentially data and variational parameters. And I will talk about this a bit later in the talk. There are actually various types of models that we can define depending on how we encode data into the model, how this is processed, and I will present this in more detail later. And as I said, these were applied in basically all areas of machine learning, be it supervised, unsupervised, or reinforcement learning. So now that we have defined this very general idea, what kind of research can be done? One way is to just empirically test this approach on benchmarking tasks in machine learning. I personally come from reinforcement learning. That's what I've studied mostly in my PhD. And there, what we investigate is the use of these parameterized quantum circuits to play benchmarking reinforcement learning tasks. And the idea is just to take a deep reinforcement learning algorithm where this should be classically a deep neural network, replace that by a parameterized quantum circuit, and try to train that and try to adapt the learning algorithms so that it works with parameterized quantum circuits and see what happens. And empirically, what we find out is that for very small parameterized quantum circuits, here we have number of qubits between 2 and 6, and the gate depth, which is in the tens of gates, we manage actually to get pretty decent performance. This is very comparable to what you would get with a simple deep neural network. And yeah, this is kind of promising for as an empirical confirmation that these methods can work. But the other side we can also take is kind of more theoretical. We know that quantum computers will probably have better performance in some tasks. Can we try to import these quantum advantage claims into a machine learning scenario? And maybe this will tell us that actually parameterized quantum circuits could have an advantage theoretically in some machine learning tasks. And yeah, to dig a bit more into that, we should see where we can actually find quantum advantages, and under assumptions we can claim that. And for that, it's nice to take a complexity theory perspective. So here, P is essentially classical algorithms that run in polynomial time. BPP is just you add a bounded error to that algorithm and some randomization. So this is what we would consider to be the class of classically efficient algorithms. PQP, on the other hand, is what you consider to be quantumly efficient algorithms. And then you probably know of NP, which is a class that contains seemingly hard tasks. And yeah, one of the big millennial problems is to show that NP is different than P. And that's still unproved, believed to be true, but unproved. And yeah, when we talk about a quantum advantage problem, is one that would lie essentially here between BQP, but not in BPP. And turns out that we don't have any unconditional separation results there. All the results that we know are based on assumptions. For instance, the assumption that factoring is classically hard. But we do know that there is Shor's algorithm for factoring. So this for sure is in BPP, but yeah, we believe that it's not in BPP. Another assumption would be that the polynomial hierarchy does not collapse. So the polynomial hierarchy is essentially starting from P and doing the step to NP. You can do this step again, generalize this step, and make a hierarchy of stuff that stays in P space, but just becomes more and more complex. And we believe that this hierarchy is actually has separation and is not actually contained in a finite level, and it just grows indefinitely. And for instance, random circuit sampling or boson sampling, the proofs that they are hard are boiled down to the assumption that indeed this polynomial hierarchy does not collapse to a finite level, 2 or 3. Yeah, so now in machine learning, the idea is to try to get these tasks that we believe to be hard under some assumptions and try to encode them into a machine learning problem and show that essentially a parameterized quantum circuit that would use quantum algorithm that can solve this problem could be successful in these machine learning tasks, and that any classical learner that would manage to solve these machine learning problems would eventually contradict these assumptions and therefore cannot exist. So let's see an example of how this is done. This was essentially a paper that came out in 2021 by the IBM group. And what they look at is essentially a task constructed out of the discrete logarithm function. So this function is just mod very large prime P, and is believed to be classically hard to compute, and is actually widely used in cryptographic protocols. And on the other hand, Shor's algorithm, when Shor's algorithm came out, it was the Shor's algorithm for factoring, but there was also Shor's algorithm for computing the discrete log. So we actually know of a polynomial time quantum algorithm to compute the discrete log. And the idea behind creating a machine learning task that embeds this function is to start essentially in log space. You will take this space mod P and randomly sample polynomially many data points and nicely linearly separate them with a nice hyperplane in the space, such that actually in this space, everything is very easily classifiable, right? Finding a linear hyperplane is very easy. But what we do now is we apply the inverse of the discrete log, which is the modular exponentiation, which is a classically efficientable computable function. And this kind of plays the role of encrypting data into a space that seems now randomly labeled to a classical observer or a classical learner. And this is actually where we now define our machine learning task. So the learner is given data in this space. And if it's a classical learner, it will look as if it's randomly labeled. Whereas for a quantum learner, it can take data from here, apply the inverse operation using Shor's algorithm, and now everything becomes linearly separable. And you can make all of this stuff more rigorous. You can actually design a parameterized quantum circuit that uses Shor's algorithm in dealing with the data. And then this part of the circuit is just taking care of the linear hyperplane that needs to be learned. And you get your quantum learner. And on the other hand, for the classical hardness, you can show that if you were to have a classical learner that achieves a non-trivial performance in this learning task, meaning that it will have, from training data, learn to classify new data points better than randomly, marginally better than randomly, then out of that learner, you can construct a classical algorithm that will compute a discrete log. And this we believe to be hard, therefore you get your contradiction. Yeah. And yeah, the purpose of this talk is try to understand what other types of claims can we make, such as this one, based on complexity theory, on the prospects of quantum advantage with parameterized quantum circuits. So yeah, here to kind of introduce the motivation behind our work, I want to just go quickly through how a quantum machine learning model would actually be used in practice. So I would distinguish two phases. The first is the training phase, and the second is the deployment phase. In the training phase, we're essentially given a data set. So a bunch of, you can imagine images, for instance, that are classified with your favorite classifier, like images of cats and dogs or whatever you prefer. And what you want to do is train your model, which is in our case defined by a parameterized quantum circuit, to best fit this unknown function g that is implicitly classifying the data. And you would do this by embedding your training data into the parameterized quantum circuit and using your favorite optimization algorithm to train the variation parameter theta, such at the end of the training phase, you get a trained model f theta star. Now, what happens after this is you stop training and you will start using your quantum model on new data X. And now I want you to imagine a scenario, for instance, autonomous driving, right? You have trained your autonomous driving model, and now you have to deploy it on, say, thousands, millions of cars. Well, the problem is that because you have a quantum model, you will still need access to a quantum computer in order to evaluate all this data that comes from thousands or millions of cars. And well, this is a problem because in any foreseeable future, we won't have enough quantum computing power to handle all of this, right? So this kind of motivates us to answer this question. Can we actually design quantum machine learning models that are trained quantumly, but evaluated classically on new data? And what we want to allow in between this training and deployment phase or evaluation phase is what we call a data collection or shadowing phase. And what we mean by this is essentially, after we found our optimal parameters theta star, which should be a theta star, we will allow running a bunch of circuits on a quantum computer to collect some data, classical data, that we can then feed in to a classical algorithm together with the new input data. And this should be guaranteed to approximate the trained function that we got at the end of our deployment phase, right? And for some reasons that will become clear later, we call this type of model where we have data collection first, that is independent of new data, and model evaluation here, classical model evaluation, we call these shadow models. Okay, so now that we have defined what we want, it turns out that concurrently to our work, some colleagues in Berlin already gave a proposal to construct such shadow models. And their approach is based on this. The idea is that, parameterized quantum circuits generate functions that have a very nice Fourier series representation, where the Fourier spectrum essentially only depends on the encoding gates that you used in your circuit. And the Fourier coefficients will, corresponding to that Fourier spectrum, will depend on the rest of the circuit, essentially. The variational parameters, the topology of the gates, and everything else, right? And the idea is just by querying the quantum model on a quantum computer, they just learn these coefficients, right? You just query it on lattice, for instance, and then you do Fourier transform, you will get your coefficients. And now that you have all the coefficients that you need, then you can just evaluate this function on any new input data. And this is what we call Fourier shadow, since it's based on the Fourier representation of the model. So what is the sample complexity of this approach? How many times do we need to query the parameterized quantum circuit in order to learn these coefficients? Where there are some nicely behaving parameters here that depend on the observable and the precision that you want. But there is one parameter that comes to become quite big. Well, essentially, it's the max frequency that you have in the spectrum. This can be nicely behaved. For instance, if you use Pauli encoding gates in your parameterized quantum circuit, use 1 per input data, then this is just going to be 2 or 3. I don't remember exactly. And the problem is that this scales exponentially with the dimension of your input data. So it seems like this approach can have some downside in sample complexity in the worst case. And we actually showed this rigorously, and I will show this later. But what seems more important here is what this paper also thought of is comparing the performance of a quantum model in a machine learning task with that of a very simple classical model, where you just take this expression and you say now that these coefficients are the free parameter of your model. You just let them freely directly be parameterized, and you just train variationally on these coefficients. And this is what they call a classical surrogate of the original quantum model. And what they found in practice is that when you actually compare the performance of the quantum model to the classical surrogate can really very well outperform the quantum model. So it seems to say that you don't really need the quantum model in the first place, and you kind of lost all quantum advantage, possible quantum advantage. So this led us to revisit our questions. And more precisely, we wanted to know whether shadow models can indeed achieve a quantum advantage over fully classical models where quantum computer were never used. Second question is, does there exist quantum models that do not admit shadow models? They cannot be written in this data collection, then quantum data collection, classical evaluation picture. And spoiler alert, we show that both of these questions can be answered by yes. Okay, so a bit of background on quantum machine learning models. I told you there are different models that can be used. And these will essentially depend on how we encode the data and process it. One class of models that was quite popular is that of explicit linear models. These are essentially done by first encoding the data in a fixed manner, and then having the variational processing and measurement. And this is data independent. And these are linear models in the data encoded quantum states, right? Now, another form of linear model is so-called implicit or kernel model, where the role of this weight matrix now is just a linear combination of data from our data set, right? And the free parameters are just the coefficients of this linear combination. And the quantum kernel comes in by essentially evaluating the overlap between two data points, rho x and rho xm here, or x prime. And this can be done from this circuit, which is complexity overlap between quantum states. And yeah, these both are linear models. And on the other hand, we have kind of a generalization of the explicit model that comes here, where we interleave data encoding and variational processing, such that it's not clear how we can separate a fixed data encoding from a data independent processing, no matter how you divide the circuit. But in this paper, what we find out is that if you give us a data uploading model, we can give you a mapping that rewrites it into an equivalent explicit model. So a linear model where the data encoding happens all first, and then everything else is variational processing. And yeah, for the purpose of this talk, the only important thing is that it tells us that it's enough to just look at linear models. You don't really have to care about data uploading. Everything can be just rewritten in the linear model picture, right? Maybe this is a good time to ask for questions if there are any. Please feel free to interrupt. Okay, I assume that everything is all right. Yeah. Mm-hmm. Yeah, okay. So what we mean by a linear model is essentially we have a feature encoding, meaning we go from data point X to some feature vector, in this case, a quantum space row of X. And then this is processed by, you can imagine as a weight matrix, or in this case, an observable that is independent of X, right? And this is essentially what you get in this case. You have a row of X, okay, the encoding from X to row of X is not linear, of course, but then after that, the processing of row of X is entirely linear. That makes it a linear model, right? In this case, data uploading, trivially, it's not clear that you can do this, but by applying some gate teleportation gadgets and stuff like this, you can actually manage to recover this linear structure for a different row prime of X, different encoding row prime of X. Okay. Okay. And now actually we introduce yet another kind of model in this paper, which we call the flipped model. And the best way to visualize it is for an explicit linear model, we just have this linear inner product between a data encoding state, row of X, which is a quantum state, so PSD trace 1, and a general parameterized observable, which just needs to satisfy being Hermitian, right? So this is how we define an explicit model. And we define a flipped model, which is just mathematically flipping the role of the quantum state and the observable. We want that the quantum state now is a parameterized state that is data independent, and the observable to just be a general Hermitian matrix that encodes the data, right? So we're not claiming that given explicit model, we can remap it to an efficiently evaluatable flipped model. Actually, this is very wrong, and we have counterexamples in the paper. What we're claiming is that instead of starting by defining a model as an explicit model, start by defining it here. So design your ansatz such that it has this structure from the start, right? And why are flipped models interesting in our case? Well, remember how a shadow model looks like. After we have trained it, we will have this shadowing phase where we evaluate a bunch of quantum circuits that depend on the parameters. And then we have a classical deployment phase that comes after. Now take a flipped model that I had before and remove the data processing observable. Just take the parameterized quantum state. And let's say we apply some random measurements. For instance, random Pauli measurements. And let's say that we designed our flipped model such that our observables O of X all belong to linear combinations of local Paulis, for instance. Well, then we know that this protocol with random Pauli measurements and for this class of states will allow us to construct so-called classical shadow of rho theta that will allow us entirely classically to evaluate all the expectation values of any observable of this form, which we are guaranteed to obtain because we define our model this way, right? So this is just to give an example of why flipped models plus classical shadows could be an interesting avenue for designing models that be quantumly trained and classically evaluated. But in general, you're free to design your flipped model however you want. You just need to design essentially a measurement procedure and design your class of data-dependent observable such that you can actually construct a classical shadow of this rho theta that can later be used to classically evaluate your data entirely classically, right? And yeah, the nice way I like to picture it is essentially what we're creating here is just through these quantum measurements, some classical advice through a quantum computer that can be used by a classical algorithm later on to evaluate all the data that it could potentially see. Yeah. So what you just care about is, yeah, kind of the data distribution somehow, or what can the data be? Um, so yeah, you will have to restrict your observables in general, right? There is no known classical shadow that will be compatible with any observable that you're gonna get in any, right? So you need, yeah, sure, but that will be an efficient classical evaluation later, right? So you want to care about something that is efficiently implementable, and then this puts kind of restrictions on what you can do. Yeah. Yeah, and the restrictions will come from your data distribution and how you encode them into observables. Okay, so now we are in position to answer our first question: can actually shadow moles have quantum advantage? It turns out that if we take the discrete log constructions from the IBM paper, we have problems into making shadow models where we first cannot flip the model and get an observable data encoding observable that is classically evaluatable, because it essentially relies on Shor's algorithm. So we kind of screwed there. And yeah, the proof comes later. Okay. So this is just to give you intuition why the flipping doesn't work. And then I can show you why you can actually not get a shadow models for those specific circuits later. So what we do instead is we turn to a different cryptographic primitive. We switch from discrete log to discrete cube root. And this is essentially just a special of the RSA function for a specific power of 3. And yeah, instead of a 1 prime now, we get n to be a semi-prime, so a product of 2 large primes. And our encryption function becomes the cube mod n function. And the hard decryption function is just the inverse, so the discrete cube root. Right? So it's the same construction as before. But the additional property of the discrete cube root is that it has a trapdoor. Essentially, if you're only given n, you can factorize it. And when you factorize it, you can compute a d that depends on these factors. And this d allows you to find an alternative, easy way of computing this discrete cube root. Right? I told you that modular exponentiation is a classically efficient algorithm, right? Now, if we're given this integer d, we can, given x, given a y here, compute y to the d, and this will be equivalent to having computed the discrete cube root, right? And yeah, as I told you, d is computable with the prime factors of it, right? But in general, finding this d is essentially hard as factoring n, right? Not classically efficient. So how does this whole help us in this shadow picture? Well, imagine a shadow model that works like this. It's a flipped model, as we start with, where this part here is just running Shor's algorithm on n, computing its factors, and from there, computing d, and also outputting the hypothesis hyperplane that we would like. And then the observable part is just essentially using this classical information and implementing this trapdoor way of computing the discrete cube root. So now, essentially, if we just take computational measurements of this state, we have all the information to classically evaluate the model on new data, and therefore we got what we wanted. We get a quantumly trainable, where the training is essentially just finding S after doing the decoding. Quantumly trainable model that is also classically evaluatable on new data. Yes. How much what, sorry? Actually, for D, you don't need any data because everything is in N, right? If you factorize N with Shor's algorithm, you have all the information. Yeah. N is fixed, right, in this problem. Yeah, exactly. Yeah. And I mean, that's a really non-trivial part of this quantum state. The trivial part is S, right? But without the D, you cannot have a good guess for S anyway. So, right, it's kind of a tricky situation. So S is just the hidden hyperplane that we randomly select here to define the learning task, right? And that, yeah, that you also need to learn from data, right? That's the only thing that you need to learn from data. N is kind of a given in the learning task. Yeah. Any other question? Yeah, Matthias. The observation behind this entire slide, you mean? Oh, so yeah, so instead of a discrete cube root, yeah, we use essentially the same construction for the machine learning task, but instead we use the, instead of the discrete log, we use the discrete cube root, and that has this trapdoor property that we can exploit in our quantum model, right? So, yeah. Yeah, exactly, yes. So Shor can find the trapdoor, and then we have all the information that we need classically then to evaluate on new data. Whereas for the discrete log, since we don't know of any trapdoor, yeah, this cannot be done, at least from this perspective. Yeah. 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 Essentially. Yeah. So you need the data to learn S, right? But that can be done entirely classically once you factorized N, right? So the hard part is just finding the D, and everything else is easy afterwards. But I mean, this is also the spirit of what quantum models are good for instance, in kernel methods. Once you find the right feature encoding, everything becomes easy, right? So yeah, once you have found a feature encoding that is efficiently implementable and is specific to your task, everything is easy, right? And essentially what we're doing without the kernel method, we're doing it in the variational processing way. Once you found the right D, right, from N, everything becomes easy, right? It's similar in spirit. Yeah. In this case, exactly. Everything becomes classical. Yeah. Any more questions? Yeah. Yeah. So the parameters will be essentially encoding S, right? So there is indeed a parameter that is left, right? It's still a learning task behind. It becomes classically trivial once you know D, but still a learning task. Yeah. Okay. Okay, so now a view from complexity theory. Yeah, by looking at the shadow models, we essentially look into an intermediate type of model between fully classical and fully quantum models, right? And we have these inclusions, and now we're wondering if they're strict, what we just showed. Yeah. In this case, yeah. 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 So we're not using classical shadows. That's why I said what we call a shadow model is just a general picture that we have here. It doesn't have to be using classical shadow or anything. It's just a way to extract classical description of a state. Exactly. Exactly. Yeah. Yeah. Yeah, exactly. Yeah. So then you're more going to heuristics and stuff like this. Like we didn't find a way of making use classical shadows in this example, and we actually didn't need to. Just a computational-based measurement is enough, right? But in general, yeah, in more general task, you would need something more elaborate. And yeah, so what we showed with this previous example is that we indeed have a separation between classical models and shadow models under the hardness of computing the discrete cube root or of factoring, essentially. And yeah, this kind of led us to define a new complexity class. We call it BPP/QGEM poly. What we mean by this is just bounded error polynomial time classical, but aided with some advice that has polynomial size in the input X and is generated efficiently by a quantum computer, right? That's what we mean by this. And this is trivially included in different complexity classes that were studied before, such that, for instance, BPP/poly is where you don't have a restriction on how this advice can be generated. It can be given to you by God. And this is a very powerful class. And we know that through a de-randomization algorithm that is actually equal to p/poly, so you can get rid of the random bits in BPP and just put everything in the advice, essentially. And now a bit about terminology. Yeah, you saw the talk of Zoe and Armando before. Why did we choose the term shadow model and not just classical surrogate? Because we really want to emphasize that we are actually using a quantum computer to generate this advice. Whereas for us, the classical surrogate is something that doesn't use a quantum computer at all. It's where you would just have a classical description of your PQC, for instance, and you would just classically try to estimate expectation values of what this PQC would give you, and that would not need a quantum computer. It would just be in BPP. So a shadow model for us is something that actually makes use of a quantum computer to generate advice for the classical algorithm, right? Okay, so now the remaining question here is, are quantum models so that cannot be turned into shadow models? And yeah, the answering this is actually pretty easy. You can very easily construct a quantum model that is universal for BQP. Just take your encoding gates to encode a bit string X and have a general polydepth unitary that follows it and a Z1 observable. This, of course, can be used to encode any function in BQP, and therefore this quantum model is universal for BQP. But now imagine that indeed this model could be turned into a shadow model. So that would mean that this BQP complete model is indeed in BPP/QGen poly. And this, in theoretical complexity perspective, means that BQP would be contained in P/poly, since this is a subfamily of P/poly, right? And this is believed to be very unlikely in complexity theory. If you don't trust me, maybe you trust Scott Aronson. And actually, we can take specific examples of functions that are in BQP but believed not to be in BPP and do the same reasoning behind it. For instance, we can take the DLP parameterized quantum circuits that I showed you in the Liu et al. Construction. And if these would indeed admit the shadow model, then we would get that this DLP problem is in P/poly. And this is also believed to be not true in cryptography. We don't believe that there is an advice that can help you do that. Yeah. So you can make the same argument with the learning problems because you have the reductions essentially. If you have a learning algorithm, then you will have an algorithm that computes the discrete log or whatever big function, and then everything will work out still, right? So you can make the argument in both because you have reductions from the learning to the actual problem behind. Discrete log, yeah, exactly. Yeah, just computing the discrete log. Does this, Giacomo, this answer your question from before? How to show that essentially this discrete log construction from IBM cannot be turned into a shadow model? It's still, yeah, it's still based on assumption. Yeah. Yeah. Yeah, I believe not to be true, and then so this is the inclusion. Just that the discrete log is not believed to be in P/poly, so polynomial time with advice. No. The above one neither, but it would be very unlikely because we don't believe that these things are indeed contained in P/poly, right? We do believe that BQP can things where advice won't really help you. Yeah, that's the only insight I have to give, unfortunately. Okay. Well, yeah, so this kind of completes a picture. With assumptions, we can show separations between all classes that we saw before. So I'm already quite far in my talk. I think, I'm not sure I will have enough time to talk about everything else here. I just want to mention that, yeah, this problem that we saw before with this Fourier approach to create a shadow model, yeah, it turns out that we can make a construction where we kind of show that this exponential sample complexity in the dimension of x, the input x, is required if you just want to take a kind of a black box approach on your quantum model to learn the Fourier coefficients. And yeah, it's very easy to do with essentially a Grover oracle-like function for the parameterized quantum circuit. I can answer this during the lunch break if you really want to know how it's done. Yeah, I will just skip this. It's not necessary. And yeah, this will have to be a very speedy explanation. Now I switch essentially gears and talk about the second paper, where instead of looking at general separations between BQP and BPP, what we look is essentially the shallow depth regime. We want to look into things that can be computed in, say, constant depth, irrespective of the input size. And yeah, the relevant classes are essentially NC0 and QNC0. So we have an arbitrary input of size n, and we always have to deal with a constant irrespective of n. And the classical class is just NC0 is just defined as constant depth classical circuit with bounded Fannin gates, such that a gate cannot have too many inputs. Essentially, there have to be a constant number of inputs, but arbitrary number of outputs. And for QNC0 is just constant depth quantum circuits where the qubits are one out of two qubit gates, can have arbitrary topology, doesn't have to be nearest neighbors. But essentially, importantly, we not allow arbitrary measurements with arbitrary feed-forward operations, because this could allow you to cheat and essentially hide complexity in the feed-forward. But for simple measurements and feed-forward, we can simulate this with a quantum circuit. You just defer the measurement to the end and replace classical controls with quantum controls. So these are the two classes we would like to show separations with. And the cool thing is that we can unconditionally show separations based essentially on the non-locality of quantum computation. You can essentially, doing bell type kind of non-locality, create correlations in your output that you cannot do in constant depth with a classical circuit. You can violate the non-locality, right? And yeah, the task we consider here in this second approach is that of distribution learning. So we're promised that we're going to be given some data from some distribution that comes from a certain complex concept class. And we define our hypothesis class, which is just candidate distributions that will fit this unknown distribution. And we measure our learning performance with essentially the TV distance between our hypothesis and the target distribution. And the interesting thing in our setting is restrict our hypothesis class to come from a restricted computational model. So either NC0 in the classical case or QNC0 in the quantum case. Now, to show learning separations, what you need is two properties, the quantum learnability part and the classical hardness. By quantum learnability, what we define is the class of quantum circuits in zero that will generate our distributions through computational-based measurements, and a learning algorithm that, for a given error and probability of error, will return the right parameter that will achieve a low error, given a polynomial number of data and training time. For the classical hardness, we will look at something weaker than the hardness to learn, which is just, or stronger, sorry, the impossibility for classical constant depth circuits to even represent anything close to the target distributions, right? So we don't have to bother much with showing hardness learning if these things cannot even represent anything close there. And we are mostly taking advantage of this previous paper from Watts and Parham, who showed an unconditional quantum advantage from sampling with shallow circuits. There, the family of distributions that they look at is slightly more complex than this one. I won't get into the complexity, it's just that you essentially have a uniformly sampled bit string of size n, and one bit that computes essentially the Majmut function. You just take the Hamming weight of x, right? Mod p, you look if that Hamming weight is larger than p over 2, lower than that, right? So this distribution, essentially, the intuition behind it is that this last bit has a kind of a global information about the uniform bit string. And therefore, this correlation intuitively should not be easy to represent with classical circuits with constant depth because, yeah, it's a complicated correlation. But quantumly, what we can use is non-local resources like the JZ state, right? And this is very helpful in computing these kind of correlations. The problem is that in QNC0 in constant depth, we cannot prepare the JZ state, and this is proven. And the trick to remedy this is to look in a poor man version of the JZ. So, for instance, a way to construct this is to take this linear cluster state, measure every second qubit in the x basis, and then what you get out on the remaining qubits is just a JZ with bit flips, essentially. So instead of 0, 0, 0, 1, 1, 1, you get a random bit string z that depends non-trivially on the outcome of these measurements and its complement, right? So it just has additional randomness that is hard to undo in constant depth. And this is actually enough to capture enough correlations to represent this function. That's kind of the trick. Yeah. 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 Yes. And I mean, if you actually use the information from these measurements, you could undo the z that you have here. It's just bit flips that depend deterministically on the outcomes. Sorry? Exactly, yeah. We don't want to cheat and use complicated board. So in constant depth, you have to deal with a random poor man JZ, right? But that turns out to be enough to represent functions of this form, or close to this at least. Okay. For the classical hardness part, here essentially it mostly relies on a previous result from Viola, showing that these types of distributions need at least log n depth to be expressed classically. So we're talking about constant versus log n, and yeah, computer scientists will tell you for all practical perspectives, log n is constant, but that's the best we can hope for in this type of regimes. And yeah, this proof essentially relies on the locality or the few bodiness of the correlations as a function of depth of classical circuits. And with log depth, that's kind of what you need to get into the required correlations to represent this function. Yeah, one problem that they had in this paper is that they only show the existence of this circuit. They don't really have an explicit constructions to be able to represent these distributions. This is actually what we spend most time on trying to show, and we didn't really manage. And I will talk about this in the next slide. Yeah. Yeah, so what we did is essentially try to extend from one function to many functions so that there's actually a learning problem behind it. And we do this by essentially shifting the Majmut function with an unknown shift that we find here. And what this turns the learning problem in is finding this hidden shift. And again, we find this hyperplane picture where the hyperplane is trivially defined by the separating step function. The only complexity is that effectively we don't have, I told you we look at slightly more complicated distribution than this. And one of the complications is that we don't have a perfect step function. What we have is like a cosine that approximates it. And what this does is that the labels here are not deterministic, but probabilistic. So we kind of have to deal with a noisy support vector machine where every point here has a certain probability of being heads and tails. And we kind of have to average out the noise to find the right hyperplane. But we show that, yeah, this can be done efficiently in P. And this is efficient in N, essentially. Right, so the upper problem that we left out is that there is no simple explicit construction for this shallow quantum circuit to represent these distributions. These circuits look like this, where the poor man JZ is given here. And what it relies here to create these correlations between the x's is a bunch of controlled rotations, but you have kind of a weird non-unitary one that comes at the end of the ladder, which kind of goes back in time. This is a very non-unitary operation. But what they show is that for large enough M, this ladder can be approximated by a unitary gate. But yeah, they don't really have an explicit construction for it. They just tell you that mathematically it exists, and then we know of compilation algorithms that work for any matrix given that is close to unitary, and this will give you essentially a large number of gates in the size of the unitary, which yeah we try to solve and try to find an explicit construction, but we were quite unsuccessful. And at the end, we just conjecture that you don't really need this ladder structure and everything. Potentially, this circuit already, we just have one controlled rotation, should be enough to get a learning separation or just a separation in sampling. But yeah, the tools are very complicated and very tricky to deal with, and this was yeah, turned out to be tricky to prove. And yeah, with this, I will just quickly conclude. We looked into this shadow model picture and showed separations between shadow models and classical models, quantum models, and shadow models under some complexity theory assumptions. As an outlook, yeah, it would be nice to try to implement this in practice and see how they perform on potentially empirical tasks. And yeah, to think about new designs for shadow models. We didn't really investigate this too deep for now. But yeah, it would be nice to think a bit how to design a measurement that is compatible with certain classes of observables. And yeah, in the second part, I told you about these unconditional separations we can show in shadow depth. It would be interesting to make clear that our explicit construction here is indeed leads to a distribution that is hard to learn classically or hard to represent classically. And yeah, it would be interesting to investigate the impact of noise on the hardness of learning. Okay, with this, I would just like to thank my co-authors and thank you for your time.
Yeah, I was just yeah, so thanks for the talk. I just wanted to ask if you ever thought of like regarding the predictive model, I have like applying algorithms similar to classical shadows, but related to observable, so the freedom of the
So you would learn the observable, and then what you would put in a state, quantum state that is classically simulatable, and then yeah, that would be an interesting direction. We didn't really think about this. Yeah. Yeah, but that's yeah, that should be quite inefficient, right? It's like trying to do. It's even more complicated than unitary tomography. Yeah. Uh, yeah. 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 It would be nice to chat about this. Yeah. 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 Yeah, we don't have any example like this, and it seems a bit tricky to really make it meaningful that you really need a quantum learning algorithm that really deals with the data. Like it seems like you can always get around with finding a easy classical algorithm and just hiding the data such that it's classically easy to interpret, right? So you really have to define what is a proper quantum learning algorithm to really make this question specific, right? And give it sense. And yeah, you kind of get into a yeah, kind of a wormhole or a black hole of yeah, things you have to define. But happy to talk about it as well. Yeah.
Yeah, that's a question actually about one of the first slides.
Mm-hmm.
When you were considering the quality gradient for the like reinforcement,
yeah.
Why do you need the reinforced algorithm? Because as far as I remember, the reinforced algorithm is a classical gradient to be able to express the gradient as a something over something.
Yeah.
But in the quantum case, can't you just use the parameter shift to avoid that entirely?
So So what you want to what you want to optimize is really the value function, which is just a sum of rewards weighted by a probability. You can do numerical differentiation of that, which is not going to give you the parameter shift rule. It's just going to give you essentially numerical differentiation with just SPSA or whatever on the thing. And then, if you really want to exploit the actual gradients of your policy, you're going to have to use something like reinforced algorithm. And the actually in computing, I don't have the slide, sorry. I don't know if it's going to show up like this. No. In computing this gradient of the log policy, we do use the parameter shift rule there. So it's actually where it appears, right? It's just that you have another step on top with the non-dynamics that you have to deal with that don't allow you to use complete differentiation through the whole value function. You just have to differentiate. You can only differentiate analytically your policy, and then you have the one part that comes that you don't know. And there, either you have to use this reinforced algorithm, or you have to make the whole thing numerically differentiable. Yeah. Okay. Thank you.